Okay, so last class we saw what is the fixed point. Okay, what is the fixed point of a map? So fixed point of a map, the map fx, okay, or like say xn plus 1 is f of xn given by solving this simultaneous equation x star equals to f of x star. Now this is true for any dimension of the map. Now you can see, if I should better write it, like if you see, this will work if you have more than one dimension. Okay, if it is a two-dimensional, solve two simultaneous equations. If it is, solve three simultaneous equations. Okay. Anyway, so we saw like how graphically you can approach it. Graphically, it means it's the point of intersection. Graphically, it's the point of intersection. The point of intersection of curve y equals to fx and y equals to x. Is it clear? So we have equated x star equals to f of x star. Okay. So if you do y equals to fx, plot it, and you plot y equals to x. So the point of intersection, you that at that point of x star equals to f of x star. So therefore, graphically you can find fixed points. Okay. Now, can a map cannot have a fixed point? The answer is yes. Can you give me an example? What you do? Yes. So you can, since you know that a curve, the function has to intersect y equals to x. So if a function doesn't intersect y equals to x, then the map doesn't have a fixed point. So therefore, any curve or fx parallel to y equals to x doesn't have a fixed point. Okay. Right. So one of the main objectives is the study of the behavior of the orbits nearby the fixed point. That means if you have a fixed point here, okay, in your phase space, in your phase space, then we want to understand if you start somewhere nearby here, W points. What happens if you start nearby? If it is a stable fixed point, these trajectories nearby the fixed point here in black will converge towards the fixed point. If your fixed point is unstable, then any near point in a neighborhood of those fixed points, if you consider further iterates of those points, will move away from. Okay? So this is the graphical understanding of stability of fixed points. Okay? So I'm not sure if I have drawn this orbit. So yeah, let us see this one. Last class we saw this one parameter bifurcation diagram. So I told you that this case, like you see, this is the fixed point here. This is the fixed point here. Fixed point. And for each parameter value r, you have a single curve. Okay. Now, why is it a unstable fixed point? It is a stable fixed point. Okay. Else, if it is an unstable fixed point, you cannot see this. Okay, you cannot. If you want to locate unstable, but you have to use sophisticated route finding methods. Right? Because this you can easily, stable points you can easily locate. Why? Because suppose this triangle, this blue point is a stable point. You can locate stable fixed point because any nearby trajectory you choose, further it reach to that stable fixed point. Okay. Therefore, wherever you start, you iterate your map, you are likely to reach the stable fixed point. So therefore, it will plot the stable fixed point. Now, suppose you have an fixed point which is in red. This is unstable fixed point. Show that there is an unstable fixed point, but if your equation is pretty complicated, you might not have a analytical solution. Okay. In that case, how you can find it? You can't find like you did for stable fixed point. Why? Because suppose you take any initial condition here, then keep on iterating your map again and again. So nearby points will be repelled away. Okay. What will be the scenario? Suppose this is the initial away from the fixed point. So these are the further iterates. It will move like this. You can see the difference. It will come like this towards the fixed point, but here it is moving, repelling away from the fixed point. So therefore, you can never look at this bifurcation diagram. How you can look at? You have to use one, like for my example, I will show you that I have been locating unstable or saddle periodic points by using Newton-Raphson method. Okay. And yeah, you can find any route possible for a given nonlinear function. Okay. So therefore, using Newton-Raphson method, you can compute stable, you can also compute unstable, but you don't need that sophisticated, because this any initial point, the further iterates will go or come. Therefore, you understand what I'm trying to say here. Okay. So therefore, analytically, understanding stability of fixed point is important. So this is the graphical approach. This is the graphical approach. Okay, for fixed points. Fine. Now we will look into how you can analytically compute fixed points. Okay, like stability of fixed points. So let us do this thing. Yeah. That before I go to a bit of analytical stuff, like analytically motivating you to find the stability, something known as a cobweb diagram, and how cobweb diagrams can help at this point. Okay. So just this is the approach here. Okay. So this is the logistic map. You can easily see, maybe this is the logistic map. It passes through the origin and it is an inverted parabola. Okay. This is the curve y equals to f of x. Okay. This is the map. Now we are considering the map xn plus 1 is f of x. So what you do, this is the curve y equals to fx and you plot y equals to x. The points where they are intersecting are the fixed points of the map. So can you tell me which are the fixed points of the map here and here? Yes, here and here. There are 2 points. Okay. Let us call it A and B. And say the point B is the fixed point. Our aim is to recollect or analyze is the fixed point stable and to understand if the fixed point B is stable or not. So what we do, we start from any initial point. So cobweb diagrams are very handy only for one-dimensional maps. Only for one-dimensional maps. This is a great technique, very, very useful and powerful technique for one-dimensional map. But as you increase your dimension, okay, that means this cobweb diagram is not useful in the case of 2 dimensions or 3 dimensions. So this is a one-dimensional map we are considering. So how to do or make this cobweb diagram? You have to listen very carefully to me here. Okay. Observe what I am telling here so that you can understand how this is going. This may be illusion to some of you. Okay. This for 2 to 3 steps. First step is to choose an initial point. Choose an initial condition. Choose an initial condition or like the starting point. Okay. First step. So here, what is our first step? X naught is our initial condition here. This is our initial condition. IC. Okay, this is our initial condition X naught. We are starting from here. Okay, fine. Everybody with me on the same page? Yes. Then next, what we do? Next, step 2. Move vertically. Move vertically. Move vertically till the function curve. Fine. Can you see now where we are? So you have started from here, X naught, which is denoted in red. Then you are moving vertically on the top. And I told you, you hit the function curve. Function curve. Is it this line or the curved line? Curved line. Okay. Y equals to fx. So this is the function curve. So you hit here, isn't it? In the blue point. Fine. Everybody okay with that? Yes. Now, the third step. What you have to do? Can you tell me based on the figure? So you have to move horizontally. Okay. So move horizontally. Follow the path. Move horizontally till you hit y equals to x. Okay. Can you see? We were in the blue point. Now let me choose another color. So move horizontally from that point. Okay, move horizontally from that point till you hit y equals to x curve. Okay, x straight line that is here. Fine. Then now is the repetition process. The end of the scheme. Okay, the 3 steps you need to choose again and again. You again have to do repeatedly till that's it, nothing else. Okay, then something magical happens. Okay, what happens here? You started from here, start from an initial condition, move to the top till you hit the function in the blue point, then move horizontally till you hit y equals to x. Okay, then you are in the magenta point. Okay, what happens there? Now this is same as in the red point. This is the case. This case is the same as the red point, isn't it? So what you do here, just to make you aware, just you can draw a line here. It is like a new initial point now. So what you do, repeat the step 1. So what is step 1 in your notebook? Proceed upwards till you hit the function. Fine. Then again, move horizontally till you hit the of y equals to x. Again move upwards. Again move y equals to x. So on. What are you seeing? It is proceeding in this way like a ladder diagram. Okay, it's like a cobweb, and it's approaching the fixed point at the point B. So you and what I told you here, can you say now is the fixed point B stable or unstable? You see that when you started from any initial condition here and you iterate your map again, cobweb diagram, you are reaching the fixed point B. Point B is like a sink. Okay. So repeat this process. Conclude now that fixed point B is stable. Fine. aware why this works. Can you tell me why this actually works? So this is a graphical approach. It is fine. Why it worked? What is this point? Suppose let us name this small a. What is the coordinate of small a? Coordinate of small a is x naught, comma f of x naught, isn't it? Are you getting it? Of course, because you are hitting the point here on the curve y equals to fx. So therefore, the curve length will be f of x naught. Okay. So indirectly, you are iterating the map. Otherwise, what you would have done, start from x naught, iterate the map f of x naught, again, so on, see the behavior of the map. Okay. The same thing you are doing just by the diagram. Now tell me what is, suppose this is B. What is B? Point B. This guy here is, suppose C. This is f of x naught, comma f of x naught. Isn't it? This might get complicated. So be on the same page. Can you understand why this is f of x naught, comma f of x naught? If you just x, so both of the coordinates should be the same. Okay. So in that sense, since this length is f of x naught, so this length is f of x naught, comma f of x. Fine. Okay with you? I urge you to find the point coordinate of point B. It should be f of x naught, comma. Huh? How many of you could not get it? Then I can say it again. No, we don't know. We don't know if it is, see, it is looking like a parabola. It can be some other function of parabola. Okay. It can be equals to 5x square. It can be y equals to 2x square. Huh? Right angle triangle. Finding the points. We are just finding the coordinates of the points. That's it. And I am telling you that why actually you went ahead and converged to the fixed point B. Because indirectly, point A is like evaluating f, which is iteration. Point small b, if you compute, see, this is f of x naught, the x coordinate. When it hit the curve y equals to fx, it is evaluating f. Are you getting that? So therefore, point B is f2 of x naught, the y coordinate. Similarly, this point C of x naught, so on. So therefore, the more you do, you're actually iterating the map, nothing else. Yeah, but this is the standard method. This is known as the Cobweb diagram. Sorry. Yeah, this is a standard method for one-dimensional system. Of course, you can take any angle you want. Why? Because if you have x naught, this straight line vertically upwards and hitting the curve y equals to fx gives f of x naught. If you take some other line, it might not hit at f of x naught. Yes. So what he was asking is, did you get started from one point? Why are you moving vertically? Why not like this? Is it at an angle? Is it? Yeah, if you do at an angle, then can you find this point? Can you find this orange point here? Iteration is more difficult at every iteration, isn't it? You have to find what angle you made here, then find what this point using trigonometry. A lot of difficulties. But how you will get this coordinate here? You can draw parallel and vertical, fine. But to that point. So how can you find? You have to compute the angle, you have to find the cos, or you have to find lines, the cobweb lines. Yes, yes. Yes, that's why it is easier to visualize. Okay. So that's a good interpretation. Okay. So if you see like yeah, these lines are parallel to x and y axis. So therefore it is more easier and more convenient and efficient to find the further iterates of the point. Okay. Fine. Okay. So this actually, Cobweb actually helps us to evaluate the orbit of x naught. Okay. Cobweb evaluate the orbit or the further iterates of x naught. Okay. Got this idea? How? If you understand this orange line, then you understood this method properly. Bit more attentive, actually. I've used so many colors to make you. Anyway, so see, simple fact. I think let me try one more time, isn't it? Let me try one more time, and this time I will draw it by hand. Okay. What I have here. Oh no. I want to know the phenomenon that is causing this. So y equals to y and x coordinate. No. So this you have this straight line here. Okay, this is y equals to x. Fine. Now let me draw the curve y equals to fx. Why? This is xn plus 1 equals to f of xn. This is the curve here. This is the iteration function for it. So you have to draw y equals to fx. Draw y equals to fx. Suppose for the sake of clarity, fine, not a good looking parabola, but a parabola. Okay, to fx, fine. Now, what are the fixed points of this map? Can you tell me? What are the fixed points of the map graphically? What are the fixed points of it? Huh? Where is B? The top, 1 point, and yeah. So this is A, this is B. Okay. Suppose we want to understand, we can understand the fixed point A. We don't know the function. This is just a sketch. Okay. What we do? First step, see your note. You have written down the steps, isn't it? First step, choose an initial condition. Suppose I chose an initial condition here, x naught. Yes, I can choose, or you want somewhere else value here. Then next step, where you want to go? Move upward, move vertically upwards till you hit where y equals to fx. So how we will draw? Yes, you hit here. Fine. Now the next step is move horizontally till till you hit y equals to x. This point. Again, you repeat it. Again, move vertically because this step is similar to the first step. Okay. So this step, you move vertically upwards again. You reach here. Fine. Then what you do? Then move horizontally again. Okay. And hit here. After that, what? You just go vertically. Hit here again. So how you're moving, can you see your trajectory? Yes. Let me draw a few more to convince you. Yeah, the yellow one, then the gray one. Then again, it converges, it will hit the fixed point here. So you can see anywhere you start. Now you start from here, again you repeat, again it will be reaching the fixed point B. So since, and I told you each of these points, A, B, C, D, and all other points are actually the iterates. Why? If you take x naught, what is the point A? Since this is lying here, this will be f of x naught, isn't it? So the coordinate of point A, I'm saying, is x naught, comma f of x naught. You got it? This is the coordinate of A. Now, what is the coordinate of B? Since this is f of x naught and you're moving horizontally and you're hitting y equals to x. So both the coordinates should be the same because it is y equals to x. So this, therefore, it should be f of x naught, comma f of x. Fine. Now you're moving ahead. Now you're moving. Previously, x naught, the hitting point was f of x naught. See the pattern. Now the starting point is f of x naught. So what should be the hitting point? The hitting point B should be f of x naught, isn't it? So therefore, coordinate of B is f of x naught, comma f of x naught, that is f2 of x, isn't it? What is point C? So B is f2 of x naught, right? You went here. So this is f2 of x naught, comma f2 of x naught. Now, if you go up, what could be this? F of f2 of x naught, isn't it? So whatever f is there, you just apply another f here. X naught, you apply f here, f of x naught. F of x naught, apply f here, f2 of x naught. F2 of x naught, apply f3 of x. Got the pattern. So C is f2 of x naught, comma f3 of x. So now you can see these points are basically the iterates. These points are basically the iterates of the map. I told you, you start from x naught, then you iterate the map f, you get x naught, iterate again, you get f2 of x naught, iterate again f3 of x naught. Our job is to find the behavior of this trajectory. The same thing is being done by the Cobweb. Now I think you got the idea. Okay, good. So now we will see a Python code. We will see a Python code to do this step. Let's see. Okay, so we will see computationally. We will see computational Cobweb diagrams. Okay, and can you give me, your job would be to see from your next class, can you give me the parameter R values where you want to see the Cobweb? Okay, understood. Because you wrote it down in your notebook, the values of R, at which period doubling was occurring, where fixed point was there, where chaos is there. You already know it, isn't it? So I ask you, just give me the parameter values, okay? And we will see different kind of Cobweb diagrams. Yes. So I am taking the logistic map. I am taking our well-known logistic map. I am taking the parameter R to be 1. Okay. From your bifurcation diagram, which you have already, at R equals to 1.5, you have a stable fixed point. Okay. And if you run the code, you will see that yes, this is the Cobweb diagram. Okay. The blue one is the logistic map. The black line is y equals to x. You started your initial condition from here. I should have drawn a straight line here, but think that it is 0.1 initial condition. We can check that initial condition also. That is in your hand to fix. Suppose you wanted no. Suppose I want more, 0.05. Let us see. It will take more number of iterations. If you go away from the fixed point and you run the Cobweb, it will take more number of ladder structure to reach to the fixed point. Okay. So see this. Yeah. It's running. Okay. Now you see, now it took lot of different ladders to reach, isn't it? as compared to the previous step. And you see that this point is the fixed point. If you zoom in here, you can easily see that it is converging to the fixed point. Okay, and the fixed point is the intersection of both blue and black curve. Fine with you. Okay. What happens if 0.4? Let us see. Yeah, that is also a good question. So what if you start opposite of the fixed point, like on the other side? Let us see. Interesting. So if you start at 0.4, you can see below the origin. We can try, but here you can see maybe this is a bit of opposite of cobweb diagram. Okay, cobweb is usually up, but you are now seeing cobweb is actually down. Okay, I suggest this case you try in your notes. Okay, maybe we can discuss, or maybe you can take a bit of time to analyze. So as you suggested that we start from negative x-axis, say minus 0.2. So I changed my axis labels, axis sizes, and you can see when you start from negative 0.0 and do that cobweb diagram, it is actually falling apart. And most interesting thing is the gap, the distance in between, you see the gap is increasing. The triangle, the size is increasing. It is diverging very fast. Okay. So that claims that 0 is an unstable fixed point, isn't it? Because we started from the positive nearby 0 point, it went to point B. Okay. We started from negative uh, 0.2 and we saw it is diverging. So therefore, what can you claim? You can claim that you can see from here, let me draw this visually. When you started from origin, okay, when you started from 0, okay, like 0 minus 0.2, it was diverging on this side. And when you started from 0.005, it went to point B. So you can see the behavior of nearby trajectories at the origin. So therefore, you can say this fixed point is unstable. Since point B, suppose you took a point here and you saw that it is converging to this point, okay, you took some point here, okay, and you saw that it is converging to this point. So therefore it is a which fixed point? Point B is which fixed point? Stable fixed point. Okay, so you can see that this point B is a stable fixed point, point A is an unstable fixed point. So I hope this concept is clear now. But as he suggested, always you cannot draw cobweb diagrams. Always in a class, if you are sitting, you cannot draw this nonlinear function. Parabola, so you were able to draw. If it is some 0. Sine x into the power x something function, cannot draw if you don't have a laptop. Then how we will solve for stability? That we will look. All right. Let me come back to my thing. Can you tell me what are the my 0 to 1? Let me make this 0 to 1 again. But you are welcome to play here. You are welcome to play with this. Okay. Can you give me another value of R? Please give me another value of R. 1.5 we had set. From your notebook, from your previous classes, can you give me another value of R and we want to see the fixed point? Now we have done fixed point. Now you saw period 2 point also exist, isn't it? Period 2 point also existed. Period 4 point also existed. Also existed. Don't you want to see how they look in Cobweb? So tell me the parameter values. 7. Okay. Let us take 3.7 and see. Okay. So this is something unintuitive. Okay. 3, at 3.7, at 3.7, you have chaos. Okay. In cobweb diagram, chaotic attractor will never settle. Your points will always oscillate. Okay. That's the time series we saw last time. Okay. Can you see why the cobweb looks like this based on the time series? In the previous class, I had shown you this was the chaotic time series. This was the chaotic time series. Why it was chaotic time series? Because you cannot predict where the next point will lie based on the previous points. Okay, fine. So this is the same chaotic time series we are. So if you want to look into the cobweb of the chaotic structure, it should not repeat also. Right? If you regular structure, then it is repeating itself. But chaos never repeats. So therefore, here for the 3.7 diagram, for r equal to 3.7 structure, and it's still not repeating. It's still not repeating. How many iteration you tell, it will still continue, keep on going. Okay. Let us see if you want to understand that concept. How many iterations? 100 iterations. Shall I do 1,000 iterations? If I do 1,000 iterations, you will see that it will fill the region in a dense way. Okay. Yeah, how much more like you want to do? See, there are some gaps here. You might say, yeah, there are some gaps here. But I will make you realize that these gaps will also be filled. Sorry. So since these gaps are also filled, mark gaps here. Mark these gaps. I will increase the number of iteration and see what happens. It will take a bit of time because we have increased the number of iterations. Yeah, you can see now. Chaos is never settling. It will always keep on oscillating. Like it will never repeat itself. So if it is never repeating itself and it has to be at a certain region of the space, then there is no choice. One is interested in their books. Somewhere it is written chaotic attractors are dense. Chaotic attractor are dense. Okay, so this means what is dense? Okay, this is the chaotic attractor so far. Any other point? 3.7 we went too far. Can we take some other point? 2. Let us see 2 at what we'll get. Taken r equals to 2, but instead of 100 iteration, I have taken 5,000 iterations. Can you see now? See, with 5,000 iteration also, it is converging to the fixed point because fixed point exists there. Slowly, we have to increase the r value. Can you tell me some more r value? You must have written in your notes. At which point periodic point exists? Tell me that. Hmm? Yeah. Uh, there. Last time you wrote in your notebooks. 4 suppose. Still converging to fixed point. How much? 2.8. Yeah. Slowly you will see it is a bit difficult to see because you are considering the transients also. I think I will leave it to you. So you have to remove the transient. If you want to understand the structure more deep, you have to discard the transient from the start. Okay. Now you can see it is converging to some periodic orbit. Okay. This is 5,000 iteration and still did not fill up the space densely. So it is a periodic orbit. It is repeating itself. The structure is repeating itself. Therefore, it's like that. Okay. Now your job is to find whether it is which periodic orbit. Okay. In exam, you might get a question with this figure, okay, with some figures, say asking you what is the period of this. Okay. This point, is this a chaotic attractor? Is this a periodic point? Then it's a which periodic point? Okay. This is left for you to explore. The figures will be given to you in the exam. 4 figures side by side. Identify the type of attractor it is. Okay. Actually, this thing will be more clear if you discard all these initial points. If you discard all these initial trajectories which are transients, then you will be left with only the periodic orbit. Then it will be easier for you to understand which period this orbit is. The orbit is of which period. Fine with you? Okay. So this is what I wanted to cover.